In this session, I shall talk about trigonometric ratios for obtuse angles. Now we know about the meanings of sines, cosines, and tangents from a right-angled triangle like that, in which if I call this adjacent side to the angle, if I call it x, if I call the vertical side opposite the angle y, and I call the hypotenuse r, we know that sine of the angle is defined as the opposite over the hypotenuse. Cosine of the angle is the adjacent over hypotenuse, and tangent of the angle is opposite over adjacent. So that's the basic meanings of these trigonometric ratios. But this also means that they are only meaningful, alright, as they are defined here. They are only meaningful if the angle is acute. We can see from this triangle. What if the angle is obtuse? If this angle is more than 90 degrees, we can't draw a right-angled triangle with an obtuse angle. So does it mean that we have to give up on these ratios? We just can't use them? Okay. Well, these ratios are too useful to throw away just because the angles are more than 90 degrees, and there is a way to extend these meanings to angles that are more than 90 degrees. The way to do it is, instead of defining these ratios using a triangle, we define it using the xy plane. So that's x-axis, y-axis, and we're going to define the angle theta as the angle between this line r and the x-axis. Then I can actually take over the meaning. We can take over the meaning of these equations and draw a right-angled triangle here, like that. Okay, then using this right-angled triangle, the sine, cosine, and tangent can have exactly the same meaning as they were defined using the right-angled triangle. So that's the start. Now then, we are going to say, right, in the right-angled triangle, we think of x and y as the sides, as two sides of the triangle. But on the xy plane, we're not going to think about x and y as just the sides of this triangle. We're going to think about x and y as the coordinates of that point, x, y. Meaning I'm going to think of x as the value of the x coordinate and y as the value of the y coordinate. Now they have the same value, alright? The coordinates and the sides have the same value because that's how we understand the xy axis. That's how we understand this graph. So they have the same meaning as far as we know. The useful thing about thinking of x and y in this way is that if we now say that the angle is more than 90 degrees, so let's have a look at what happens. X and y. If the angle is more than 90 degrees, then it is somewhere there. That's the angle. That's the length r. If I now think about this point, which has gone from there to there, I can continue to think of the coordinate of this point as x and y. So even if the angle is now more than 90 degrees, I can still find values for x and y. Okay, so x will be the value there and y is the value there. But this time, of course, x would not be the sides of a triangle anymore. X is just the x value, the x coordinates of this point. And you can see that because x is on the left of the origin, this is now a negative number. And of course, if we just look at x as the side of a triangle, it has no meaning if x is negative. Alright, the length of a side has to be positive. But because we are now extending the meaning or generalizing it to mean the coordinates of this point, we now make it possible for x to have a negative value. So that means that when we generalize the meaning in this way, alright, we would not think about x and y as just the sides of a right-angled triangle anymore. Now if we look at this picture, I can then say that we can still make use of these relations, right? But we should now take the x and y as the coordinates of this point. So in this way, the trigonometric ratios can still have meaning even for obtuse angles. Okay. Now, then suppose now that we want to find the value of, say, cosine 150 degrees. How do we do that? Now we can of course draw a picture on the graph and actually measure the length of these sides and find the x and y values. But it is usually convenient if we can express this, or if we can find this in terms of the cosine of an acute angle. Because if we have the cosine of an acute angle, then we can always imagine drawing a triangle, measuring the sides, and then finding the cosine by doing x over r. Okay, so for this and sometimes for other reasons, it is useful if we can express this in terms of the cosine of an acute angle. And there is a way we can do it. If we look at this picture again, so although we now have an obtuse angle, and we couldn't actually use the definition for the right angled triangle directly. If you look at this picture, notice that it still has a right angled triangle down here, only that the angle theta, this obtuse angle, is not one of the angles in the acute angle. Alright, but the obtuse angle is related to this angle. This angle is just 180 degrees minus theta. As you can see, that's a straight line. Now, and I know that if let's say this is 150 degrees, then this would be 30 degrees. Alright. So, is there some connection between cosine of 150 degrees and the cosine of 30 degrees? Well, if you look at this, cosine of 30 degrees is the length of this side, which is adjacent to this angle, divided by the length of this side. Okay, but cosine of 150 degrees is the coordinates, the x coordinates of this point, divided by r. Now the x coordinate of this point has the same magnitude as this side, but it is negative because it's on the left of the origin. So in other words, there is a difference in sign between these two. Alright, this is obtained from just taking the length of this side and dividing by this. This is obtained from x, which is negative of this length, and divided by this. So the two should be related by the minus sign. So we can turn this understanding into a formula. Now let me write out, use theta instead of 150. So what I want to do is to find a connection between this theta and the cosine of 180 degrees minus theta. So cosine theta, we know, is the coordinate x divided by r. What about the cosine of this acute angle, 180 degrees minus theta? Okay, it would be the length of this side over r. Now, the length of this side is not x, as we have seen, because x is a negative number. But the length of this side is the numerical value of x without the sign. Okay, so since x is negative, I can cancel that sign if I say minus x, right? Because if x is negative, then minus of x is positive. So therefore, this gives me the length of this side, and dividing by r gives the cosine of this acute angle. So now, if I compare these two, you see that this is x over r, this is minus x over r. So therefore, this has to be the negative of that. So finally, we have proved that cosine of an angle is equal to minus of the cosine of 180 degrees minus theta. Now the nice thing about this formula is that it is true even if the angle is not obtuse. So for example, what if this angle is acute. Does this formula still work? Well, if this formula is acute, if it's less than 90 degrees, then you'll find that this angle, 180 minus theta, is now obtuse. Alright, this would now be more than 90 degrees. So therefore, the two would still be related by the minus sign. Okay, so although we have derived this formula, assuming that theta is obtuse, we find that this formula can actually be used for any angle. Now, extending this idea now to the other trigonometric ratio, sine and tangent, we can find corresponding formulae. So let's start with sine theta. So we look at sine theta. Now, according to this definition, sine theta is y over r. It's the opposite over hypotenuse. Now, sine theta, here, for the obtuse angle, would be the y coordinates, right? Because now we need to generalize the vertical side, the opposite, to the y coordinates. So if you take this y value and divide by r, we would get sine theta. Sine theta is y over r. Now, following the same idea here, I want to know what is the sine of that angle, that acute angle. So that would be 180 degrees minus theta. So since this is the acute angle, I can follow the original meaning of sine and take the opposite, which is the vertical length, divided by r. Now, the vertical length in this case happens to be the same as the y value, okay, because the y value here is positive. So the vertical side is still y. Therefore, this is y over r. Now, if I compare these two equations, you see that both sine theta and sine 180 minus theta are equal to the same y over r. Therefore, sine theta is equal to sine 180 degrees minus theta. And in the same way as for cosine theta, although I have derived this using assuming that theta is more than 180 degrees, this relation is still true even when theta is smaller than 90 degrees, because if this is smaller than 90 degrees, it simply means that 180 minus theta is more than 90 degrees. So this becomes obtuse. Okay. Now let's finish off with obtaining the relation for tangent theta when the angle is obtuse. So we see from here that tangent theta is y over x, right? Vertical over the horizontal sides. And if we look at this obtuse angle, it means that tangent theta is the y coordinate divided by the x coordinate. me write this down. Tangent theta is equal to y over x. So now I want to find tangent of 180 degrees minus theta. So let's look at this picture. Now we know from the definition, the original definition, that tangent is opposite over adjacent, right? The ratio of those two sides. So now if we want to look at 180 degrees minus theta, we're looking at this acute angle. So we can look at this triangle again, this right angle triangle, and say that the tangent of this angle is equal to this side, this vertical side, divided by the horizontal side. Now the vertical side is equal to y, because y is positive, but the horizontal side is not equal to x because x is negative. But if we put a minus sign in front of x, then it becomes positive and we can use that. So therefore, the tangent of this angle should be y divided by this length, which is minus x. Y divided by minus x. Now if we compare these two equations, we see that this is negative of this. Okay, so therefore this must also be the negative of this. So we have our relation. Tangent theta is equal to minus tangent 180 degrees minus theta. Okay, we'll stop here.